Good morning, everyone. We are from the Department of Computer Science and Engineering, Punjab Engineering College. Uh, our team members for this project are myself, Amit Singh, and my friends Rohan Lathar, Akash Talyan, and Pushkar under the guidance of Dr. Nitin Kumar. Our major project is titled Mitigating Bias in Medical Datasets Using Neural Networks with SHAP for Feature Importance. The problem we are addressing is bias in healthcare AI models. Medical datasets often overrepresent some groups and underrepresent others, causing models to make unfair or inaccurate predictions for certain patients. To solve this, we built a neural network for stroke prediction, used SHAP to identify which features influence predictions the most, and applied SMOT to handle class imbalance and improve fairness. We used a brain stroke prediction dataset from Kaggle containing 4,981 patient records with 11 features such as age, BMI, glucose level, hypertension, gender, and smoking status. The dataset was highly imbalanced with only about 5% stroke cases. For pre-processing, we handled missing BMI values using the median, converted categorical features into numerical from using label encoding, normalized numerical features using standard scalar, and performed an 80-20 stratified train test split to maintain the same class distribution in both datasets.
Hi, I am Akash Talyan and I will be explaining the neural network model we built for stroke prediction. We designed a sequential neural network for a binary classification, predicting whether a patient is at risk of a stroke or not. The model has 5 layers. The input layer takes 10 preprocessed features, 3 hidden layers follow with 64, 32, and 16 neurons respectively, all using ReLU activation. The output layer has single neuron with sigmoid activation, which gives a probability between 0 and 1. Above 0.5 means stroke risk, below 0.5 means no risk. For compiling model, we used binary cross entropy as a loss function and Adam optimizer with a learning rate of 0.01 for efficient convergence and a dropout rate of 0.2 to prevent overfitting. ReLU is computationally efficient and avoid the vanishing gradient problem in hidden layers, while sigmoid is the ideal choice for binary classification output. Tools used include Python, TensorFlow with Keras for building the model, Sharp for explainability, Skitlearn for pre-processing and matrices, and Google Colab for GPU-based training.
Let's discuss about SMOT, resolving class imbalance. Now let me talk about one of the key techniques we use, SMOT, which stands for synthetic minority oversampling technique. As we discussed, our dataset had a major class imbalance problem. Only 248 out of 4,981 records were stroke cases. This means the positive class stroke makes up less than 5% of the data. When we train a model on such imbalanced data, the model becomes biased towards the majority class. It learns to always predict no stroke because that's the safe bet. It gets the right answer 95% of the time, but it completely fails due to detecting actual stroke cases, which defeats the purpose. SMOT solves this by generating synthetic samples for the minority class. Here is how it works. It picks a minority class sample, finds its k nearest neighbors within the sample class, then creates a new sample by interpolating between the original and one of its neighbors using the formula x new equals ixi plus lambda times the difference between xj and xi, where lambda is a random number between 0 and 1. After applying SMOT, our stroke class went from 248 samples to 474,733, perfectly matching the non-stroke class. The key advantage of SMOT over simple duplication is that it creates new realistic data points instead of just copying existing ones, which reduces the risk of overfitting. So next we applied SHAP analysis to understand which features were actually important for our model's predictions. We used SHAP's Deep Explainer, which is specifically designed for deep learning models. The results were very revealing. The top 5 features by mean absolute SHAP value were age at 1.847, BMI at 1.523, average glucose level at 1.201, and various other values. So our model was learning the right patterns. However, at the bottom of the list, we found features like work type, ever married, marriage status, and other such features with very low SHAP values. These features were not contributing meaningfully to prediction, but they could be introducing noise and bias into the model. So we made decision to remove these few features and retrain the model on refined feature set. This is an important step. We are not just blindly removing features. We are using SHAP as an evidence-based tool to make informed decisions about which features to keep and which to remove. So this slide shows the actual SHAP plots from our analysis. On the top left, we have SHAP summary plot. Each dot represent a patient. The color indicates feature value. Red means high, blue means low. And you can clearly see that average glucose level and age have wider spread, meaning they have the most impact on prediction. On the right side, we have feature importance bar chart. This ranks feature by their mean absolute SHAP value. Age and BMI age interaction are at the top, while hypertension and heart disease are at the very bottom. On the bottom left is the force plot for single prediction. This shows exactly how each feature contributed to one specific patient's prediction. Some features pushed the prediction towards stroke, showed in red, and some pushed it away, shown in blue. This kind of per patient explainability is what makes SHAP so powerful for clinical applications.
Now let us look at the results after applying bias mitigation. The important metric for our project is recall, because in healthcare, missing a stroke patient can be very dangerous. Before mitigation, the recall was 0.62, which means the model was missing many actual stroke cases. After applying SMOT and removing biased feature, the recall improved to 1. This means the model is able to identify all stroke patients. Now looking at the accuracy, initially the model has accuracy of 91%, but since the data set was imbalanced, this value was a bit misleading. So we have to, uh, after mitigating, the accuracy increased to 95%. And this improvement is more meaningful because the model now performs well for both classes. These are the confusion matrix before and after bias mitigation. In the first confusion matrix, the model correctly predicted most known stroke patients, but it missed all 54 actual stroke cases. These false negative are a serious issue in the medical application. After mitigation, the model correctly identified all 138 stroke patients, and the false negative reduced to 0. The metrics table also show the clear improvement. Accuracy improved from 91% to 95%. Precision improved from 0.78 to 0.91, and recall and F1 score has also improved. Now, contribution to SDG. Our project contribute to UN Sustainable Development Goals. First is SDG 3, good health and well-being. Second is SDG 10, reduce inequalities. Then is future work. For future work, we would like to test this framework on large and most diverse healthcare dataset from different hospital and medical condition. We also want to explore more advanced bias reduction techniques and develop a clear user-friendly system that doctors can easily use in the clinical settings. These are some references we have used, and thank you and have a nice